Did I do the infinite plane? You know what? I don't remember. I think I actually did. Now I'm realizing I think I did actually do this problem. The infinite plane was the last one that we did for the electric field. And we got that for the insulator, the non-conducting infinite plane. Yeah, we did that. The electric field is E is equal to sigma over 2 epsilon naught. The field. It's a constant field. And it would have to be moving along. I think in our case, it was horizontal. So I just do the magnitude, but it was, along yeah, we just do the magnitude. I want to check that real quick with, posted the lectures already. I'm going to just pull that up and check real quick to make sure that modules. Oh no, I haven't posted it yet. Week 6. My bad, I need to do that. Could go and check it here. That would have been October 2nd. Yeah. Cool. Cutting off the top. Oh man. Yeah, I did that. Yeah, that solution sigma over 2 epsilon is there. Okay, well, good. I'm a little bit farther ahead on today's lecture than I thought. So I think that means we can go ahead and start the next chapter on potential, which I think is chapter 24, maybe. Let's take a look. Lead you guys in. Here. There. This is shortcut here. Modules. Book. Yeah, chapter 24. So Gauss's law is 23, and now we're going to enter into 24. Planar spherical. So they ended with spherical. Start listening. Yeah, we did all these. Charge, isolated conductor. Oh, you know what? I guess they do talk about it in that chapter. Somehow I thought they talked about it. So this is the thing I needed to talk about while I wasn't doing the conductors. Okay. I should have looked at my notes. Charge, isolated conductor. Let's just take a look now. Yeah. Interesting. Gauss's law of surface. So that section is important in order for us to be able to apply Gauss. And here's the thing I was about to do. So that's for the surface. So I'll go ahead and do that now. Yeah. So there's some more. I guess they do tell you, but you really need to. I think they get to potential electric potential. They revisit this. And I was thinking that it was introduced in the next chapter, but they do talk about it here. Okay, well, it was good that I looked. And then I maybe go back and do a couple more Gauss's law, basically the same ones that we did, but with a conductor. And so we need to have that section in there. I'm glad I looked at that. So, okay, so we got that solution, and I'm going to do what I call it rectangular. They call it planar symmetry, which is actually the first that they, I guess, do. But before we discuss that, let's talk about talk about conductors. So we've already talked about it a little bit about charging, how to charge a conductor. We charge conductors both with induction and conduction. You might want to go back and take a look at that section. And the only thing that I said about the charge at that time is that once we charged a conductor, charge redistributes itself on the surface of the conductor. And it does that, remember this argument that I've been making about using the analogy of the Borg in Star Trek. And it's not that when you place charge on a conductor, it runs around the surface or inside, like flows and kind of moving away from one another. It's more like all of the charge communicates and it knows how it needs to be distributed based on this excess charge that's now on the conductor. And so different charge, it incorporates the excess charge as part of the overall free charge collective. We use that word term in Star Trek. And then the charge just behave, they take on different, essentially responsibilities accordingly. So whatever the nearest charge is to a spot where a charge needs to be redistributed, the nearest charge there just takes on that. The screen is stuck. This one? Oh, this guy. Yeah, okay. It just takes on that responsibility, if you will. We've discussed that as well. I won't go back over that. So because of that, because there is excess charge on the conductor, essentially that charge cannot, whatever amount of charge that is, that amount of charge cannot embed itself inside the object, inside the conductor, because it's excess. And there's already free charge that's inside the conductor. that ultimately will be available for current. Whenever we talk about that, a couple chapters, we put a potential on the conductor, and it's shared. I didn't go over it specifically, but hopefully from chemistry or someplace high school, you know that when a metal is formed, its shells are not filled, and so because of that, it can give off an electron in the outer shell, what's called the valence shell, and that each atom does that, and those electrons become the electrons that all atoms can use, and that's the model that we teach. We've been teaching it for 70 years, I guess, or maybe I don't know how long. Definitely since the 20s at least, but whatever. And it's part of, I guess, what we consider the standard model, which technically is a particle physics term. But yeah, and that's something we'll talk about more so in Physics 39. But that's the idea. And so none of those free charges exist outside of the conductor, and on the surface of the conductor is considered to be outside. So that's the stable, for a stable material that's neutral, has the same number of total positive and negative charges. That's kind of what we say. So whenever we charge it, we're putting excess charges other than those on the material, or we're taking some away, taking some of the free charge away from it, which then it looks like it has excess positive charges. So, because remember, the only thing that can move in material are electrons. So if something is positively charged, it lost some of its free electrons. If it's negatively charged, it gained some excess electrons. But even in the case where it loses electrons, those positive charges that are there are considered to be excess charge, because now they're excess to the total number of electrons that are there. Again, that's the model. So whenever we place excess charges on a material, now just for the purpose of just thinking about it, when we take electrons away, and so there's an excess of positive charges on the material, just really what I've told you is that that's really they're called holes. It's the absence of electrons. So we still treat them it's a mathematical concept, but because obviously the positive charges in the nucleus, so how can they redistribute themselves over the surface of the material? Well, it's the absence of negative charges that are doing that. So you have to kind of think of it that way. So still, we're only talking about manipulating negative charges, which are free charges or that can move around. These charges are not coming from the bound charges, electrons around the atoms. They are all the free charges. At least that's the way I think about it. So because of that, whenever we place excess charges on a conductor, negative charges, they cannot embed themselves inside the material. They have to stay outside on the surface because of the nature of how a neutral, stable conductor, how the charges behave. So that is a fundamental rule that excess charge always lies on the outside, on the surface of a conducting material. So that's one postulate or something we can say. Excess. How do you spell excess? Oh, yeah. Charge lies on the surface. And conductor. Okay. Now, also, because of that, we know that electric fields are the origin, and the monopoles are the poles that are associated with the electric field. So we say that electric fields originate and terminate on charges, originate on positive charges, terminate on negative charges. But remember that you have to have an excess of charge to have an electric field. Otherwise, and according also associated with symmetry. Basically, what I'm trying to say is that electric fields abide by superposition. So if you have more than one charge in an area, the electric field at a point in space near those charges will be the superposition of the fields of those different charges. But in a material, you have equal number of positive and negative charges. And remember, the charges are redistributing self within the material because of symmetry. Like charge repels, unlike charge attracts. So just like without a nucleus, we don't say that normally a nucleus has a field because the negative charges cancel out the positive charges. Technically, that's not just because they're the same amount, it's also because of the symmetry of the distribution of the charges relative to one another. Now, I know what you might say, the first thing you think about, well, the charges are in the nucleus and the electrons in the electron cloud. So just like there's a potential difference between a cloud in the earth and, in the grounded earth when there's a storm, and then there's a if it's too much, you can have lightning, which is an electric field, kind of go between. So you might think, well, shouldn't there be a field between the positive charges? Well, there's not. And that here again, that's the model says that it's neutral unless some external field comes along and shifts the cloud and causes an electric field to exist. Like when you take the balloon and you rub wool and put it on, like we talked about the polarization. But normally in the normal, what we'll call states of the charge and electron, the normal grounded state of an atom, we say there is. Now, that is very fishy to me. I'll give you that, okay? Because that clearly means that it's not exactly a cloud above a negative cloud above a positive, because that implies spherical symmetry. I mean, we're going to look at problems like that on the macroscopic level, where we have a positive charge inside and like put a positive charge, inside and this is for non-conductors, a non-conducting shell, and there will definitely be a field between them, a non-conducting negatively charged shell. Yes. So that seems to be what they're teaching me, that's what an atom looks like, right? But there isn't a field there. And, we can just chalk it up to quantum, implications that we haven't talked about yet. But it's a little fishy to me. But that said, that's why we call it, I mentioned it earlier when we talked about the nuclear forces, the fundamental forces, the four fundamental forces: gravity, electromagnetism, strong and weak nuclear forces. Well, whenever you have words like strong and weak, which are very vague, that implies to me right there in physics that there's something that we don't really know, what the nucleus is and what electrons are and what we don't. But we have these models and they work, for practically for things we understand. And this is part of the standard model that an atomic site within a material that is not being exposed to external electric field uh, is a neutral because of the cancellation of positive and negative charges and because of symmetry as well. So there are no fields associated with that unless you have some external disturbance. So because there's also no excess charge inside the material to break up that symmetry, there are no electric fields inside a conductor. No electric fields exist inside or below the surface of a conductor. The standard thing that we accept as being true. That's one deal. Excess charge lies on the surface, and electric fields do not exist inside of a conductor. And finally, the other implication of the fact that, and these are all related to this idea here that charge exists on the surface, excess charge. And the final thing has to do, well, it's not the final, but it's the next one, has to do with it's related to this. So you might say, okay, well, what about external electric fields? Like, what if you have a conductor near a non-external, near an external electric field? For example, let me take a piece of metal or this aluminum. This is a marker is an aluminum marker, and I'm going to place it so the light that I have here for the board is right here. That's an electromagnetic wave. So it's, we're dealing with static fields here, but whatever, it's a field, electric field, magnetic field. Still, the thing is, it's a wave. We can think of it as a wave. It comes, it hits that thing. If I'm inside and I have a detector, will I see that field? And the answer is no. Because if that were true, it would have to go through the aluminum, which would mean at some point, actually, that's not true. That's not a great example. You can see the field on the inside, but it's not okay. Yeah, you can detect field on the inside of the of the cylindrical surface. But as it turns out, the field does not actually penetrate the aluminum. And that might seem a little bit counterintuitive. Well, how does it get on the inside? Well, it has to do with something. Maybe I should have done an electric field. I should have probably done a static field. It doesn't matter though. But just let's say that we have some sort of metal ball here, right? I'll do a rectangular symmetry. Let's make it a solid ball. So it's metal. So it's a conducting sheet. And let's say that we have, I'll just do a positive charge. So we have a positive charge there. And we know that the field, well, just for the purpose of illustration, I'll make a constant field. But yeah, maybe it came from a capacitor plate. I stuck this, so I have a capacitor plate over here, and I made it positive. Like maybe I put this thing in between capacitor plates where I have a bunch of positive charge over here, positive charges lined up over here. Maybe an infinite plane or something, I don't know. And it's creating an electric field that is constant and it's moving like that or pointing like that. So when the field hits this surface, what you will see is that the field will appear on the other side, but it actually does not go through the material. And it's related to the idea of shielding well, it has to do with something called shielding. And we exploit this whenever we we exploit this concept for electrical devices when we protect them. You might have heard of something like a Faraday cage for large, if you're trying to shield large spaces from external fields, or even within cell phones and things, we place some sort of metallic shielding around the circuitry so that external fields and things don't damage them. But this is what happens. So we have the free charges inside the material that I've been talking about. Now I'm not going to build up the lattice, but again, here I want you to visualize what we've built up as the modified Einstein model of a solid. Right? So go back and look at that picture. All of that stuff is inside this metal, right? We've got the atomic sites, we've got the free electrons that I was just talking about earlier. We've got the bound electrons around the atoms. All that stuff is in here. Now, the only thing that can actually translate, when I say translate, again, I'm not talking about moving around in the way that like a current, remember the Borg. So when I say electric charges move to shield, it's almost like some of these sci-fi movies where you have material that, I think there was a movie that just came out, some animated movie where this kid was making these, what he calls them, but they were little metal balls that could kind of move all at the same time and form things. What movie was that? It was pretty good. Anyway, something like that where the charges, they all can kind of, when it sees a field here, it senses that the field wants to get in. So as opposed to them flowing, it's just that they kind of all behave in such a way that they shield the field from getting it. So in other words, what I'm saying is when a field comes here, it's almost like having a positive charge there at that point when that field is interacting with that surface. So positive attracts negative. So what will happen is a number of free electrons will then rise to the surface. They will rise to the surface. The visual like that I like to make are like mumps or measles or bumps coming on your surface. You'll see electrons pop up to the surface and behave like excess charge on the surface of the material. And because there's only a certain amount of excess charge, that excess charge is now on the surface and not on the inside. And so right at the inside of the material, it becomes positively charged, not because there are positively charges there, but because it's an absence of the negative electrons that just rose to the surface. And so it satisfies everything because it keeps the electric field from penetrating that surface, and therefore everything is cool. Yeah, penetrates the surface. Now, same thing over here on this side, because we had a actually, yeah, it's not gonna, yeah, so that doesn't happen there. Sorry, that's not it. Well, I guess it kind of does, but it's still considered neutral on the inside of the material because of, I guess, maybe shielding effects. What we actually say is that, yeah, yeah, I guess, yeah, it's like that. Yeah, what happens is, now here, yeah, this is a little bit tricky. It was always a bit tricky for me to understand, but this is how I'm going to explain it. You would think that what I just said happens, and it does in a sense, but then the material adjusts so that you don't see a positive charge on the inside. And this is why. Because the material needed excess negative charges on this side of the material. But on this side, it actually needs its positive charges. Why? Because the field, essentially, there's only a certain number of free charges in the material. So when on this side, when free charges rise to the surface, to keep because of conservation of charge, over on this side, the absence of negative charges rise to the surface. Or you could say that the electrons on the surface move inside. And so what we see is a positive charge, what looks like positive excess charge on the other side. And which causes the field then to continue to extend, on the other side as if it had gone through. So it's the same magnitude of the external field on the outside that was on the inside. And so therefore you see the same E field on either side of the material, but no E field on the inside. Now, I guess, yeah, yeah. So, um, so what I'm about to say is this. So what I sorry, I'm kind of fumbling here, but this is, I guess I should have, yeah, whatever. So let's go back to what I was about to say, because that's what you would expect is that, there's a conservation of charge. So if some rolls here, what happens right on the inside of the surface? Well, essentially, if I've lost negative charges from the surface, then on the inside, basically nothing has changed. Then from before the external electric field uh, ex- was interacting with the conducting metal. That is, before the metal was exposed to the external electric field. So if you have the same number of practical negative charges inside, then whatever its behavior and configuration was, it doesn't have to change. But then you might say, well, there's a problem because I get how this can act like excess charge and rise to the surface. But over here, you said there was electrons on the surface that went inside, but it's a metal. So there are no electrons on the surface. In fact, what is the surface? What do you when you talk about the surface of a metal in the inside, what is the boundary that distinguishes that? Well, here's where the thing uh, gets a little kind of weird, but kind of makes sense. There is no inside and outside of any surface. None, if you really think about it. What we're calling the surface is just the border from which the material starts. And if you think about the Einstein model, it's just the atomic lattice that just extends to a particular position and then stops. It only looks like a border in the way that we think because we can't see the individual atoms. So if you go in and look inside, there's no point where the material says, well, there's an inside and there's an outside. Material just thinks it's just the material, right? It's just where the material stops, that's where space begins or whatever. I don't know. But the surface of this material, it looks really just like the inside. It's just the end of the atomic lattice. And those electrons and everything are there. We just can't see them, right? So it looks like some sort of boundary that's different, I guess, than what's inside. And when we say inside, it's just infinitesimal distances, as you move inside the material. So the thing that I'm calling excess charges here are just the negative charges that were on the edge, maybe the bound charges, and I don't know, the free charges they go up to. I don't know what it looks like, and nobody knows. But like I don't know, maybe it would look like the ocean, and then the boundary between the water and the molecules of water, and then the top. I don't know. I have no idea. But when you really think about it, inside and outside is a macroscopic perspective, essentially, of the material. If you're a microscopic perspective, it's just the material, and then there's not. So the free charges that I'm seeing that are here is just kind of like a polarization, if you will. Maybe those atoms on the surface are being polarized because maybe the electrons, the bound electrons kind of, or the electron cloud in general gets shifted inside to kind of behave like the excess charge on the other side over here that was lost, so that collectively, I don't know. But that's basically what's happening. It's the bound and free charges on this border of the material that shift in some way, and because of the symmetry of their physical distribution, and are more inside the material than normal, so that it can behave like it's free charge and that the thing is still neutral on the inside, um so that it can be considered excess charge on the inside, and because there can be considered no field on the inside, and because of that, on the surface it looks like it has lost negative charge, and so therefore it looks like there's an excess of positive charge. So that's actually what's going on, and this process is called shielding. I before E except after C. Yeah. And that's why we can use that idea to exploit in protecting electric circuits or buildings or things like that, and we do it all the time. But it's also why whenever you go into a building and you have your cell phone, if you go into a metal container or a metal, or an elevator or something like that, the signal uh, dies. It can be much less clear than when not, because even though the field gets through, I mean, sometimes basically there's other things that are going on that we have to talk about maybe a little bit later on, where it loses energy because there's absorption of energy when it interacts with the surface and stuff. So over here, maybe the field, I mean, this is an ideal case where you get exactly the same field on the other side and not. Also, it depends on the thickness of the material. There's a bunch of stuff going on the surface whenever an electric field interacts with those surface particles. And so ideally, you don't necessarily get the same field on the other side. But you definitely will never get a field on the inside. That's not what's going on. And for a non-conductor, as we implied the other day when I derived this thing, now I didn't get this detail with the surface, but the electric field absolutely definitely goes through the material, right? So even if it's concrete, you can have a pretty thick concrete building. And you compare that to some thin, metal shell within that building or something analogous to that, and the field will still be much clearer in the concrete, going through the concrete, than through even a thin piece of metal. So yeah, so that's important to understand. um, Next chapter we will come back to this and talk about this in the context of something called electric potential. And that's what threw me off. I guess I forgot that most physics books, because there you can start to quantify things a little bit more. And so I just forgot that we do mention this in accordance with Gauss's law. And the reason is because we have to understand this when we're applying Gauss's law to a metal. So with that said, let's go back and look at a couple two problems with Gauss's law. Very similar problems than what we did yesterday, but as opposed to making it a conductor, let's make it as opposed to making it a non-conductor, which is what we did. All those objects were insulators yesterday. Let's take a look at it, with the metal. And the first one that I'll look at is the spherical distribution. Now, remember yesterday we had a spherical non-conductor, and we had placed charge uniformly throughout the whole conductor. Well, the first thing that we can say now is that if we have a geometrically uniform conducting sphere, metal ball, no matter how much charge we put on it, it can only reside on the surface. We cannot put excess charge in the surface, even if it's a solid ball. It just can't be done. So if we assume that we have a charged metal ball, a solid metal ball, we can only talk about sigma, surface charge density. We can't talk about rho, volume charge density, because excess charge will never be distributed throughout the volume of the material, because it won't stay there because of what we said. It will, the charge will only be detected on the surface of the ball, not within the volume of the ball. So whether it's hollow or whether it's solid, it doesn't matter. And that's something that the books will use as testing points. They might not explicitly say that you have a solid conductor that has charge, whatever, but you have to know that it's on the surface. So they're only talking about surface charge, even if it's uniformly distributed, it's just over the surface. So a solid metal ball is charged with sigma plus. So we then would have to just know that, like I said, the charge is positive, is distributed uniformly on the surface, and no excess charge will reside on the inside. And so it'll still have its own field, right? The field will be pointing out radially out, just like any spherical charge distribution. But the field will terminate on the surface, or originate on the surface, I guess I would say, and would not be coming from anything on the inside, unlike the insulating ball that was charged. So again, use Gauss's law to find the electric field at a point P, a distance R away from the center of that ball. Well, if this is the center, we can have this be a radial vector R, small r, and this is our point P. What we see is that we'll just go through and apply Gauss' law really quickly again. It'll give us a good chance to review. Now, let's call the radius of the ball itself capital R naught, just like we did yesterday. For this radius here is capital R naught, and the radial distance away from the center is small r, the position vector. Actually, I should make this a little bit smaller so I can draw my Gaussian surface. Not so big. So we'll make it right here. So this is point P, and we're going to call that vector R. Hopefully you can see that pretty well. And yeah, point P is here. So going through the steps of applying Gauss's law, we have to have the charge distribution. 1, you get the field distribution. 2, you choose your symmetry of Gaussian surface. It's going to be a spherical shell. You place it so that it goes to the point where you want to find the field. That's right here. So my Gaussian sphere, Gaussian shell would look like this. And, this is a cross section of it. But it would be encompassing a sphere shell. Now, the field has a flux because it permeates my Gaussian surface. And then I apply Gauss's law. And Gauss's law states that the electrostatic flux equals the total charge enclosed inside my Gaussian surface divided by epsilon naught. The flux becomes integral of E over the surface dot dA equals total charge enclosed divided by epsilon naught. All the stuff we said yesterday is still valid. So you do the dot product. dA is perpendicular to the surface everywhere. Right, dA is the direction. So like here, direction of dA is parallel to the electric field originating on that surface. And so E dot dA cosine 0, you just get E dA. E is, since I've centered my Gaussian surface over this distribution, the electric field is equal in magnitude everywhere on the surface, because we know the electric field diminishes as r squared, but it's the same distance away from the center or away from the surface technically. Everywhere on the surface. The Gaussian surface, that is the same distance away from the surface of the charge distribution. So the electric field should be the same, which means it's constant, comes out of the integral. And so we just have E integral over the closed surface of dA equals total charge enclosed divided by epsilon naught. Okay, so then we just have E A over total charge enclosed divided by epsilon naught, and then we solve for E. So here what we see is that for this guy, E equals charge enclosed divided by A, and then, okay, it's 1 over epsilon naught. But the charge enclosed is just the total charge of the material. That becomes 1 over epsilon naught, charge total over the area of the Gaussian, remember? So, sorry, not the area. Yeah, that's the area of the Gaussian. Oh, I have to be a little bit careful. Yeah, be just a little bit careful because, and I know what the area. So the area is a sphere, so the area is 4 pi r squared. I got to be a little bit careful. This charge enclosed, it's going to be. I can write that in terms of charge density because that's the only thing I know. But yeah, the charge density is. Let's go back just to keep it here. I can do a little bit better. This is the area of the Gaussian. I'll put G on here. But now the charge enclosed by the definition of charge density is just the charge density sigma plus times the area of the charge distribution, which is 4 pi r naught squared. So 4 pi r naught squared. Yeah, 4 pi r naught squared. Yeah, so then if I take 6 and plug it into here, and that becomes E is equal to 1 over epsilon naught times sigma plus 4 pi r naught squared. But AG, the area of the Gaussian, is 4 pi small r squared divided by 4 pi r squared. There you go. That's what we want. You get that guy goes, that guy goes. So what I have is E on the outside, E, for R greater than R naught. In fact, let me have to write this. Come back over here. R greater than R naught. You get sigma plus over epsilon naught times 1 over R squared. I'm thinking I did something yesterday with a non-conducting sphere and I got a constant outside. And that I might have made a mistake with that. I might have yeah. Somehow I'm having that in my mind. If I did that, I shouldn't have gotten a constant. I have to go back and look at that because I might have assumed whenever I plugged in here, I might have had sigma times A and just had a brain fart where I assumed that A was the same as that A because I might have not put in the actual quantitative value of A. I might have just called it area and got confused. That's only the case whenever that is true whenever you're right at the surface. I don't know. I don't know. I might just be overthinking it. I might have done it right. But outside, it's not, right? Because we know that the field, because this 1 of R squared has to be there because we know that when we get very far away, we can't distinguish that there's some size to this charge distribution. It looks like a point charge, certainly. And so And also we can see that the field is not constant as it moves out, right? It's diminishing. So this is telling us, right? This is telling us that the field is not constant, but that it moves out as a 1 over r squared law. So yeah, that's the answer. That makes sense. But I did tell you that on the surface it's constant, right? I told you that. So when oh, and I left off the r. I left off the r naught squared. R naught squared. I actually kind of like to write it like this. Let me do that again. Sigma plus r naught squared over epsilon naught times 1 over r squared. I like to write it like that just to emphasize to myself that this r naught is a constant because it's the radius, but this guy is not. Because as we took an arbitrary point P, but that point could have been anywhere. So, once we establish a point where we want to find the field, we can say that R is constant for that. But I always say this, I always repeat it just because I want to keep reminding you, because it's easier to forget. It was for me. But I could have chosen this point P or this point P or this. So basically, once we get the functional form, we realize that this R here is a variable. Right? So the overall field certainly is not constant, as I said, because we can clearly see that the line density is decreasing as we move away from that charge distribution. So we should get a non-constant field when we apply. And again, we could do Coulomb's law and we would get that result. But, I did this in 8 steps, which could have been 3 or 4, only 8 because I'm explaining things to you all. But, trust me, this is a 3-page problem for me anyway, when I do it with Coulomb's law. Crazy. So yeah, we get that. Now, what about, so we did 3 areas, outside, on the surface, and inside. Well, let's go to the surface. Well, when we go to the surface and we redraw our Gaussian surface, so that is it is an infinitesimal distance above the surface, still being able to encapsulate this free charge. Well, this is free charge, I guess, on this one, that we've placed on this conductor. So we're infinitely close to the surface, but not the surface. And so we do get this free charge that becomes inside our Gaussian surface. But at that point, then, the position where we are, R naught, or R, becomes R naught. So what you get, those two things cancel, right? And the field truly does become a constant on the surface. And that's what we said. We said it qualitatively here that the field is constant on the surface, which is why it was able to come out of the integral in the first place. But now we actually know its value, that on the surface, the electric field for R equaling R naught is equal to the value sigma over epsilon naught, just on the surface. And still, it's a radial because it's going to, well, on the surface, it is a constant. So, yeah, it's constant, but it's still a field. So it still has a direction, and it points out. So it's not, yeah, so it's a radial. That's the value there. And if you go even infinitesimally inside the surface and draw another Gaussian, basically, since there's no excess charge inside and and therefore it can be no field, so you're just going to get 0, right? Like when you do Gauss's law, the charge enclosed is always 0, so the flux is 0. There's no flux going through this inside surface, which means that for the inside, the E has to be 0. And that's it. So it basically, that's a way of proving this statement that I just made. But you remember, it's kind of, and it is, I think, considered a proof, but so R less than R naught, even if you're infinitesimally close to the inside surface still, since this charge is on the surface, you don't have any enclosed charge, and the field is 0. But it all comes, applying Gauss's law appropriately, essentially comes from first a qualitative understanding of how charge behaves. Because ultimately, when you apply Gauss's law, you need to know you need to be able to determine what charge is enclosed inside of your Gaussian uh, at any point where you're trying to find the field, and therefore create a Gaussian surface there. So basically, whether this is a solid conductor, but if it was a hollow conductor, you're going to get the same answers for all the different regions, because, well, if it's hollow, there clearly is no surface, no charge on the inside. And whatever charge resides on the surface, there's going to be shielding at the surface, so that field, that excess charge can't penetrate. The field can't penetrate the thing for the reasons we mentioned earlier, the shielding. So these excess charges won't be able to give any field on the inside. So for a couple reasons, you can say that the charge of the field on the inside is zero. And on the surface, same thing. It'll be constant. You get the same answer here for. And then outside the surface, you the same. So whether the ball is solid or, that's really two problems in one. Whether you have a solid sphere or a spherical shell that's charged, these are the form of the electric field for all the different regions because of the nature of the charge distribution associated with that object. Now, what the book will do is take this and play around with the thing. It'll do things like, and be a little bit careful about this. It might do something like, well, the analogy that I was just making with you right now is, an atom, and the atomic site around an atom. The whole idea of a positive nucleus and an outer shell, a electron cloud. We could try to mimic something like that, but again, it's not going to be the same because they're not quantum. But like say you have a positive charge here, like some point charge. I'll make it really small. All right. Alexa, stop trying to scare the bejeebies out of me. I don't know if you heard my Alexa popping off for some reason. I don't know why. Maybe she thought I said something. Let's say that I've got I put around a spherical shell. Could be, let's make it metallic. We could even give it like some sort of surface, some sort of thickness. And I charge it negatively. This is a nice problem to talk about. So you have a spherical, and let's say this is plus Q, and this is, well, and we can, well, actually, let's just talk about this. Let's make this, let's say that this is a neutral conductor, a neutral conducting shell, neutral metal conducting shell that I place around a positive charge. Let's deal with this one first. So we're not putting any excess charge on the shell. So again, a metal shell, metal neutral shell about a charged particle, a centered charged particle. Talk about what happens. Let me make this surface a bit thicker so I can work easily. Okay. You've got an inside surface and an outside surface. Now, this is hollow in here, right? Hollow and solid. So you can see that. Now we know this thing has a field. Now, when we say that there can be no field inside a conductor, this is a closed shell. But when we say inside, we're talking about inside the boundaries of the material, not necessarily inside the space that the object encloses. So you have to distinguish, because that's something that also tripped me up back when I was, an undergrad. That's what I was talking about over here. We're inside the material itself. But if you have a closed surface, that surface encloses a volume that is separate from the inside of the material that's doing the enclosing. Because otherwise, it would violate what we know. Like if we say there can be no field inside here, then what's happening to what's canceling the field of the positive charge? Well, there is a cancellation, but it doesn't occur inside the volume. It basically occurs at the surface, the inside surface of the conductor, because of shielding. So let's look at what happens. We've got a field here. It's a positive, charge. So the field is, it's the origin of a field, and the field goes out like so, radially. You're going to see a radial field inside there. That's a good point. I wonder. I said there were no fields, but I don't know if we've talked about that. I've never seen anything that even addressed that issue. I just assumed. Most people that the model assumes. I'm talking to myself. I'll get to that later. Um, Lost my train of thought. Yeah. So what happens is you get here, and basically the same thing I said that happened previously happens here. You get shielding. What you see is where this was a neutral, once a neutral shell, um, and it is neutral because it doesn't gain any excess charge, but it just has free charge that behaves like excess charge. You can't have this field penetrating the boundaries of the metal. So what you then see are free charges that pop to the surface that behave like excess charge in order to terminate the field. And literally, if you had a electro, uh, what's it called, an electrometer or something that can measure charge, and you can measure the inside surface. In fact, uh, the first guy who did this was Gauss. Gauss, I think. Yeah, Gauss. Yeah, he did something like a milk pail or something, which had like an open surface, so he could put like electrodes inside, but it was almost closed. It was something like, well, it's actually, I think, straight up milk pail, right? And so he saw that, you could charge the outside, but the inside surface wouldn't be charged if you put excess charge on it and things like that. Um, so the famous experiment, he's the one who figured all this stuff out about excess charge, but hence why we call it a Gaussian surface, right? Because Gauss was doing all that work back in I think it was the 1700s, I think late 1700s. But again, if it's neutral and you have charge pop to the surface and act like excess charge and nothing happens on the outside, then it looks like it's not neutral, right? It looks like you've got excess charge on the inside and none on the outside. So now somehow magically this neutral conductor became charged without it. It would be a violation of, I guess, conservation of energy. Just spontaneous charge just would appear, which ultimately would be a violation of conservation of energy. So what you then have is positive charge, full positive charge, I'll call it that, pop to the surface and pop to the surface. It's going to be the equal number of of positive charge on the outside surface as you see negative charge on the inside surface, and therefore this field can extend on just like it was, you know, just like there was nothing here. So you could look at this neutral shell and it would look just like the actual positively charged shell that we dealt with over here, because you wouldn't be able to see inside to realize that there's just some charge on the inside, right? It's really interesting how metal behaves, how these charges, how things behave. Yeah, so the thing would still be neutral because you still have the same number of full excess charge on the outside and inside surface. And there's no field that's actually penetrated the inside of the material, so that's satisfied. And on the inside of the enclosed volume, you still have the same field. Like this charge doesn't really know that it's enclosed. It wouldn't know that if it's, it would just feel like it's doing its thing, right? And giving a field in the close vicinity of the charge, just like it would if nothing were there. So that's the kind of thing. So now you'll get a lot of problems where it will ask you, what is the field? Now we have four regions. We got the outside, actually five. The outside, the outside of the object, the outside surface, the inside surface, and then the inside volume. Sorry, the outside, one, the outside surface, two, the inside of the material, three, the inside surface, four, and then the inside volume. And I'll let you do it. I would encourage you to go and apply Gauss's law at all those places. But I'm going to tell you what you're going to find. On the outside, you're just going to get this guy. To prove to yourselves. On the outside surface, you're going to get this guy. But remember, you have to use this. There's various radiuses. This has a radius, inside radius, outside radius, inside radius, and then so forth. But just work it out. On the inside, now check this out. This is interesting. You might, you got to get zero, right? But you might be tempted. You say, okay, well, I just got the one charge there because that's the only actual real charge that's there. But basically, this excess charge, it acts like real charge. So when you place your Gaussian surface anywhere inside this mirror, basically any radius that's larger than the inside radius, you're going to be encompassing two types of charge. The negative charge on the inside surface that acts like excess charge, and the other charge that you place in the middle. But remember, because of conservation of charge and the nature of charge, the only amount of excess charge that appeared on the inside surface was the value of that charge. Otherwise, it wouldn't have been able to terminate it, and there would have been a field inside. So you know that this charge on the inside surface is negative Q, having the same magnitude as that positive Q. So when you put the Gaussian surface there and you do the total charge enclosed, because remember it's superposition, you add it all up, you got negative charge here plus positive charge there, same magnitude, they cancel out, and the total charge enclosed by the Gaussian surface everywhere inside this thing in the material is zero, so that there would be no field here. When you go to the inside surface, same thing, because you're inside. So there's on this surface, there's no field. It's zero, because when you put your Gaussian surface here, the idea is that, as I said, it's infinitesimally close to the surface, but still incorporating whatever excess charge that is on that. Sorry. Yeah, incorporating whatever excess charge that is on that surface. Right. So you're getting that in. So again, when you apply Gauss's law, it's the same as what was on the inside. The total charge is going to be that excess charge there and the charge in the center. So the total charge is zero. So on the inside surface, there is no excess charge. There's no excess charge. And yeah. So zero. And then when you go for R less than R inside, of course, you go back to basically this guy. Well, actually, it's just the point charge, because here I described it in terms of charge density. And I guess actually out here, I didn't describe this in terms of charge. It would just be in terms of charge. So basically, outside, the field is going to be the same as inside, and that field would just be KQ over R squared. So out here and inside here, the field E is just KQ over R squared, R hat, because I would have given you the value of charge. Oh, and by the way, I didn't actually explicitly talk about how you add a charge here. Anywhere on the outside or on the surface, now you got three charges, right? Because remember, I'm infinitesimally close to the surface, so I'm actually incorporating all that positive charge. Remember, it's Q. It's the same magnitude as that guy and that guy. So now I've got three. I've got positive Q here. I've got negative Q here, which cancel, but then I got positive Q here. So outside the surface, I'm still at, it's basically like this thing isn't even there. So I've got the positive Q um, uh, contributing to the field, and this would be the functional form of the field outside, and everywhere inside. On the inside surface here, you have 0. On the inside of the material, you got 0. And then on the surface of the material here, you would just have basically whatever, I didn't describe this radius, but whatever that radius is, you just replace it there and it becomes a constant everywhere on the field or everywhere on the surface. So yeah, and you can just mix and match and do all kinds of things, but with cylindrical symmetry, because this, it's very similar type of deal, right? This could be a cylinder with a charged line, with a charge Q or something, and it'd be the same. My arguments would be the same as I just made, because you're looking at a cross section of the cylinder. So I usually just do this one in class, because going through that and talking about it and gives you basically a fundamental foundation for doing any kind of problem where you have charged objects within charged objects, and usually they deal with the cylindrical or the spherical symmetry, and it should be enough for you to be able to handle that. But you're going to see things like that within the chapter, or certainly within the problems but it actually, once you get a handle on it, and really, for me, the foundation was the qualitative, because you got to know how the charge is acting, how it's behaving, before you can even apply Gauss's law. You got to know that. And once you know that, it actually becomes kind of fun, because even now I kind of enjoyed this. I haven't done this in a long time, because it just gives you, I don't know, it's a good feeling to know that you have a model that works. And I think that the story isn't fully written, but this is the model that we use and it works. So, like it said using the quote from Oppenheimer, you can be a smartest person in the world and come up with a brilliant theory, but if it doesn't work, if the experiment doesn't corroborate it, then it's just a bunch of intelligent mumbo jumbo, right? And so, as Gauss showed with the classic ice pail experiment, that's what it's called, ice pail. And I said milk pail. No, sorry, ice pail experiment. It's a classic experiment where he determined that excess charge on a conductor always lies on the surface. And so Google it, the Faraday ice pail experiment. That was basically the beginning of a fundamental understanding of how charge behaves with conductors. Faraday ice pail experiment. So, my bad. I said the late 1700s. That's not true. Michael Faraday was a young man in the 1820s. So he did all this stuff between like 1820 and 1835 or something like that. He become, by the 1830s and 40s, he had become the head of the Royal Physics Society. But as I said, he was drawn, he had a lot of qualitative insights, but he didn't go to college. and he had just started off working in a physics lab, like sweeping floors, and worked his way up because he was brilliant, clearly. But it wasn't until like 1860s that a young guy named James Clerk Maxwell, who studied all of Faraday's writings, probably born in the 20s or something like that, and I think, or born in the 30s, because when he was 18 or 19, he finished college by the time before he was 20. He took all of Faraday's qualitative descriptions and writings, and he, I guess, did his own experiments as well, and basically wrote electromagnetic theory. That what we're studying, all the stuff we're studying in this course, the quantitative part. Now, not all of it, right? Because things like Coulomb's law, all those things were known, but there was no electromagnetic. Basically, we had electrostatics and magnetostatics, but we didn't have electromagnetic theory. So he wasn't able to. People thought that electrostatics and magnetostatics were two separate concepts, two separate physical phenomena, two separate forces. But it was Maxwell who took all that stuff, things before Faraday, and Coulomb's law. That stuff was actually known before Faraday, but took all of that stuff and basically formed electromagnetic theory. Um, and things like the speed of light, all that was projected in the 1860s. And we weren't able to corroborate it until about 40 years later, when we had technology and we could measure things and we could measure the speed of light. And sure enough, um, the fact that light was a wave and can be a particle, all that stuff he figured out, and we didn't test it until the turn of the century, which is around 1900s, which led to the modern physics, which I've discussed before. But yeah, this ice pill experiment was done back in the 30s, the 1830s, 1820s, 1830s. And so we've known this for quite a while. So these models that we use work. So if they work, then there must be something right about them if they're not completely correct. Yeah. Okay, so it's about break time for me here. Um, when I come back, I'm going to do one more. We have enough information to do that now. I'm going to go back to the last type of geometry that I used was planar geometry. And I'm going to go back to the thick. And before yesterday, we had a thick non-conductor that had charge, planar non-conductor that was infinite. And just think of basically an infinite wall, like a brick wall or concrete wall that we could, or a plastic wall, or something that's infinite, and we could charge it. So that's the problem we did yesterday, where we had charge all throughout the surface of the conductor. Okay. And we talked about it in terms of charge density, and it was a sigma because, well, actually, technically, it should have been a rho, right? Yeah. What did I do yesterday? I guess I did a rho. I hope I did. Or I might have just placed charge on the surface. I think I did. Obviously, I did if I use sigma. Yeah. Well, this will be the same because hmm, that's interesting. Yeah, I placed the charge on the surface so that I could mimic a conductor. I'll do a conductor now and show you that that's the same solution we're going to get. So I guess I didn't do a planar geometry where it was charged was uniformly distributed throughout the volume. Mm. Well, if it were, Yeah, well, you still have two surfaces, so you're still going to get that factor of two. It's the area there. But the charge enclosed is just going to be defined by volume, not area. So yeah, I think that with a I'll do that one too. We'll do that. I think the answer is just going to be almost the same, but where there's a sigma, you'd have to have a rho for a non-conducting, uniformly charged plane, infinite plane. Take a break and we'll come back and I'll take a look at both of those, the infinite conducting plane and the infinite non-conducting plane with uniform charge density. All right. Okay. We're back and yeah, I'm just going to finish up today with discussion of these last couple of Gauss's law problems, and then the next chapter is potential difference and capacitors. I think they discussed in that chapter as well. We'll take a look again here. Oh, we got that out. That was this. What I just discussed here was actually section 3 of chapter 23. And all the other sections we hit basically yesterday. So that's it. Chapter 3 is done. Well, it will be when I get these planar things. But then we go into potential, electric potential. And I think at the end of that chapter, they do discuss, oh no, they have it broken up. Oh yeah. So sometimes this book separates everything, which maybe is a good thing, but a lot of books incorporate capacitance in potential in the same chapter. So yeah, there's a lot there. So we'll start that basic. I'll probably introduce potential, at least define it, what it is, and then we'll and now it's not the same as potential energy. It's potential. Kind of same thing with gravity. You got to be careful about the terminology. You know, I've made it clear last semester that when we say gravity, we now have to distinguish between force and acceleration. Before you come into a physics class, it's all the same, right? But we want to make sure we use language to distinguish between that. Well, we kind of have a similar issue with potential. What you are familiar with is gravitational potential energy, but there's also electrical potential. And actually there's also gravitational potential. So there's, in terms of, let's say, gravity. So there's a gravitational potential energy, MGH, you know, simply put in a gravitational field, a constant gravitational field, you know about that. But there's actually something called gravitational potential, which we didn't talk about. We don't talk about at all on the level of mechanics, but it exists, and it is something that we talk about at higher levels. In the same way we talk about it with here, and that we're going to talk about here in this chapter. So there are two types of potential. There's a gravitational potential, which it's related to energy, but basically it's energy, gravitational energy, potential energy per unit mass. And then there's just gravitational potential energy, which is what you know. Here we will talk about both types. We'll talk about electrical potential energy. We'll define that for a constant field, and we'll see some parallels between that and gravity. That's how I usually start the chapter. But then we will immediately define gravitational potential, which is gravitational potential energy per unit charge. And I'll go ahead and make the analogy again, you know, whenever I quantify it and put it up on the board. But it's interesting that we don't do that for gravity. And I mean, we do it, it's there, but we don't talk about it at the undergraduate level. Anyway, or at the sophomore undergraduate level. Well, sophomore meaning whatever, this physics I had as a sophomore. So physics and chemistry majors and math majors get it as a sophomore. So we loosely speak of these three courses as sophomore level physics because you're done with them by the end of your sophomore year. If not earlier. So I digress, though. Let's get back to finishing this up. How much time we got? Got plenty of time. So we might actually get into defining, introducing electrical potential. And by the way, electrical potential, energy, and voltage is the, sorry, electrical potential and voltage are the same thing. Electrical potential energy is essentially energy, right? We'll talk about it. Yes, so we will do this scenario where we have let's go back to the planar geometry for Gauss's law. Yeah. Watch these things. Yeah, so what am I doing here? Yeah, I'm gonna do a planar geometry. Yeah, so you know what? I didn't do my markers. My markers are going out. Sorry. I need to freshen up my markers here. I'm gonna be in trouble. I'm gonna do a couple of these real quick. Sorry, I should have done this during the break, but some snack and basically looking at the state of our nation. Guess you've heard by now all the drama going on in DC right now. No comment. Stick to the physics. So what do we do? Let's go with a conductor, an infinite conducting plane. Okay, so I think I like to draw them something like this. because I want to give it a thickness. So you could have it thin, which is what a lot of people start with, but I'm going to go with a thick one. All right, so it's thick, has a thickness, has a front and a back. Now, because of what we discussed just now, and so goes on here to infinity, right? Goes on here to infinity, here, and here. So let's make this positive infinity. This would be negative on that side, and this is positive up here. And this would be negative down here. And so let's give it a charge density of plus sigma. So it has to be plus sigma, right? Because it can't be a rho. Rho implies that there's, if we look at so this is a front view. But this would be like a side view. So rho would imply that we have charge inside the material. Make sure, did I turn this thing on? Please tell me I did. Oh, yeah. Yeah. But if it's a conducting plane, a conductor, charge can't be on the inside. So no matter how much charge I dump on it, even if I try to force some charge on the inside, the free charge itself will behave in such a way that the charge will all reside on the surface. It'll just reconfigure itself. So you can't have charge on the inside, okay? And now what a lot of books will do to get around you having to deduce that, they'll just give you a non-conducting plane, and they'll say that the charge is on the surface or whatever. But, you know, you can have a couple different scenarios here, and I just wanted to point that out. So for a non-conducting plane, for a conductor, it doesn't matter whether it's a solid conductor or a conducting planar shell or whatever. Any charge that's going to be on it is always going to reside on the surface. So from the side view, it'll look like that. Now from this view, you wouldn't be able to tell, right? Because you wouldn't necessarily know where you only know it's on the surface, but you can't look inside. So it might be inside, it might be not, if you didn't know what type of material it was. But here, that's what it is. And of course, the field has to be perpendicular to the surface, just like it was for a point charge or a spherical charge distribution. For a planar, it's the same. So if it's an infinite plane, we would expect that the field should be, you know, constant. Like as you move away, it's going to stay the same. Now, if it were a finite deal, it wouldn't be like if it were a small sheet. Well, if you're very close to the sheet, it's constant, right? But when you get out, you have what you call edging effects. It starts to look actually like a point charge. And if you get very far away, you wouldn't be able to determine the length. So it would look just like a point charge, right? But if you have an infinite plane, what goes on, these edging effects, they kind of cross where you get none, right? And ultimately everywhere in the region you have a constant field. So I need to take a quick break right now. I want you to go ahead if you're, go ahead and see if you can, before I work it out, see if you can figure out the solution, apply Gauss's law. And we did it yesterday. It's going to be the same thing, but give you a chance to work through it by yourself. And I will be right back. Okay, let's finish this up. Yeah, so again, it's really about understanding the charge distribution and the corresponding electric field pattern. And when you're dealing with metals, it's not quite as simple as non-metals. So metal, no charge inside, consistent with what we've been discussing. And and no charge on the inside. So yeah, now we apply Gauss's law. Now Gauss's law states that the flux through a closed surface is equal to the total charge enclosed inside that closed surface divided by epsilon naught. I like to always start with that and give a little mental energy to every step of that 5-step process, just so it decreases my chances of missing something and simultaneously reinforces my ability to apply the law correctly and consistently. So I'm going to choose a Gaussian pillbox. Now, here's the thing: you got to do it. You got to be a little bit smart. So you definitely the steps 1 and 2, even though it may seem trivial once you do a couple problems because a lot of it will be the same, but anything can slightly change at any time you tweak something on a problem. And I kind of build that in mechanics when we start with Newton's laws and things and applying them the correct way. Like, don't take anything for granted. I think it's always good not to do that. So yesterday, when I had the thing full, the non-conductor, there was charge everywhere inside, but also with a non-conductor, because a field can exist on the inside, and let's take a look at that again. Non-conductor. Even if we did have charge, let's just say this is a non-conductor and we don't put charge on the inside. So it's going to look the same way, and this might be the problem we did yesterday. I'll do negative charge, let's say. So just put the negative charge on the surface. Here's the fundamental problem. We know that the field will it'll look like this, but radially inward on both sides. But the difference between a conductor and a non-conductor is the fact that charge and field can exist on the inside. So there's a field due to these charges on the inside that points, I'll put a dotted line there, points like that. Is that what's going to happen? Actually, no, my bad. There would be a field on the inside, but it's due to the shielding. My bad, that's not true. It's a little bit more complicated than that. If this is excess charge and this is a non-conductor, just like with sticking the balloon on, you're going to get positive charges here. You're going to get the polarization effect. And over here, right? Think about that. It's excess charge. Wow. Oh, no. You're going to get the same answer. And there you go. That's what I mean. I didn't think that through. It's only when it's completely filled on the inside that you get the 2 out. If it's charged on the outside, then you get something that mimics, is going to get the same solution. because as I was about to say here, you got, let's make them different colors. So we'll keep that blue on that side. So I'm gonna change the color on this side. So here you're gonna have them coming in like that, right? And you would get a field on the inside due to those charges. But let's make these a different color. Make them, they're still negative, but just we got our eye. Wow, that's interesting. I hadn't thought about that in a long time, I guess. Yeah, so that's what I mean. Just these subtle changes, you have to think through it every time. So make that negative, negative, negative. So here, sure, coming in like this, right? But if it's the same amount of charge on each side over here, that field is going in like that. So the fields are in opposite directions, so they cancel. So you're not going to have a field on the inside if you just have charge on the surface, even if it's a non-conductor, and even though field can exist. There's a superposition and you get a cancellation on the inside. Yeah. So ultimately, we're going to get the same answer. Basically, because of that, what I was about to say is that the field on this side can't contribute over here because there'll be a cancellation of the field. Yeah. If it were yesterday when we had the charge all distributed all the way through, you don't get complete cancellation for obvious reasons. And there's a contribution of charge on the inside to the other side. And so that's where the two comes from, because you have to basically take in consideration the flux, because it's not just about the charge, it's about the amount of flux going through the surfaces. So since you have two surfaces, all the charges in between those surfaces contribute to the flux of either surface. So that's really where the two comes from. It's not double the charge. We don't know how much charge is inside. I didn't specify that. It's just the flux through the surface is where the two comes from. And because there's a cancellation of the charges coming from this side going over there, the fields of these charges never actually penetrate that other side, and vice versa. So when you're on one side or the other, the field that's there is only due to the charges, the amount of charge on that particular surface. So again, just having that, since it looks as if we're going to get the same general solution, so I'm going to go ahead and take that off now. Well, actually, I guess we could do it, but we could get the same thing. But it tells you, you got to know that because you want to know how to apply the Gaussian surface. Yesterday, when we had the non-conducting completely through, we chose a Gaussian surface. Yeah, let's do it again. Okay, so what I'm saying is, if we have charge everywhere on the surface and inside, we will get contributions of flux from charges, basically over here. So we took the Gaussian and we made it like it was a pill box, but it covered the whole region. It covered both surfaces. I'm not sure it's a non-conductor again. I mean, we know it's a non-conductor because there's charge on the inside, but just to be explicit. But when we have something like a non-conductor that just has surface charge on the surface, or a conductor, which always will have charge on the surface, that is, you're not going to get a contribution from the other side when you're on one particular side, as I said. So there's no reason to incorporate the charge over there. We can just take the pill box and have it just go back. Basically, one side is going to be embedded inside of the interior of the material where the field is zero. So this is my Gaussian now. And I can choose the same type of Gaussian for this. So ultimately, then I'm only going to be incorporating charge. The only charge that will be enclosed would just be on that surface. So like here, it'll be the charge right there. And over here, it'll be the charge just on one surface. So we can almost anticipate the solution. If the previous solution was sigma over 2 epsilon, you might anticipate that we're just going to get sigma over epsilon. And also, that's the magnitude. Yeah, we got sigma 2 epsilon here. And so let's go ahead and finish out then. And here, say, I guess, this picture, a lot of times they'll do something like this and kind of put it back, and you're going to have like goes through. So that's the pillbox. I'm using a cylindrical shape. A pillbox is supposed to be a square, supposed to be a square, just because square has 6 sides, so I'd have to calculate the flux of the 6 sides. Cylindrical shape has 3 sides, so it's just easier to do that. And it goes through and comes out. Well, actually here it just goes on the inside and does not go through the other side. So this is the side view of that scenario. Okay. So these are all 3 different problems. This guy here is going to be the same. So I'll do the solution to these 2. Well, let me just do it right here. Now we're assuming that we have sigma plus sigma is the charge density for each one. This guy, and this is the same one, but also this guy. Here, because we have volume charge, this would have to be a rho, not a sigma, which is where I made the mistake yesterday, I think. I can't remember. I don't think I did it in terms of rho, but it's got to be a rho. Or maybe I didn't do that problem yesterday. Maybe I'm confusing. That's probably why I didn't, because I knew that I had to have all this discussion. And I thought that it was going to be in the next chapter. But anyway, so maybe we didn't do that. Well, I'm just going to skip to this representation. E dot dA equals total charge enclosed. And again, a lot of times, because you're adding up, you might see it written like this. Total meaning summation of all the type of charge. Now here, this integral is just going to reduce to EA again. Why? Because, well, here's another thing. First of all, you have to talk in charge of charge density here and not total actual charge, because technically there's infinite charge, because it's an infinite plane. If the charge is distributed uniformly, then you got infinite charge. But we know whether it's infinite charge or not, if the charge is distributed uniformly, by definition, the sigma is equal to, it could be total charge. Well, total charge over total area is just going to be infinity over infinity, so whatever. But if you take some finite charge, surface area, then it's just whatever that charge is. The charge enclosed inside that little area divided by, the area of that that differential area or delta area, however you want to call it. And so that's what we're doing. We're taking a little cross-section area here, and the amount of charge that's inside that is going to be equal that divided by that area is going to be equal to sigma, because sigma is a constant. So yeah, so the Q plus then, getting kind of messy here. Let's I think I can erase this picture. Let's deal with that picture. Okay, equation 1 and equation 2. And so then 3, we can say that the charge enclosed equals sigma plus times the area of my Gaussian. And so I can take 3, put it up in here. Yeah. And so I'm going to have basically integral closed surface of E dA cosine of 0, which goes to 1, equals sigma plus times the area of the Gaussian over epsilon naught. E is constant because it's the same everywhere on the surface, comes out of the integral. And so ultimately on the left side, we just have E times the area. But this is the area of the Gaussian in this case, equals sigma plus A over epsilon naught. And so obviously, and it is the Gaussian. I know in a couple other problems that you get, like with the cylindrical and spherical symmetry, you got to be a little bit careful because the geometrical nature, the areas go as the radius, and the radius changes as you move out. Here, the reason it's going to cancel out the area on either side is because when you look at the pillbox, we're actually talking about, now I need the picture. It's the surface area, the cross-sectional area. That's the area we're talking about. Because if you looked in the picture, it's a cylinder. So the amount of the Gaussian that cuts through the surface of my charge distribution is a little circle. But the circle is the same cross-section area as the top and back of the pillbox. So it's of the flux through that surface, right? It's a circle. So the same area that we're talking about of that area that is enclosing the charge, where the Gaussian intersects with the surface of the charge distribution, is the same area as the Gaussian surface through which the flux that we're actually calculating goes through. So you divide them out and you just get that the E, the magnitude of the electric field, is equal to, the areas cancel, and you just have sigma, the charge density, over epsilon naught. Now, that's the magnitude. It's still going to be a vector, if I wanted to write it as a vector, but I have to superimpose a coordinate system and give that horizontal direction. So I guess it would be positive X or whatever you call it. I'm just going to leave it as the magnitude, but everywhere the magnitude of the electric field will be constant, and that's close to the surface or as far away as you can get, as long as this is an infinite plane, the magnitude would be the same. And I kind of also did some fudging because this is just I've really got 3 surfaces, right? I've got surface 1, surface 2, and surface 3. Remember, it's a cylinder, so surface 1 is cylindrical. Well, for surface 1, the flux is 0. All right, the right side is 0 because the cosine of E, everywhere on that surface, E points radially away from the surface, and A points radially away from the surface, and E is perpendicular to the surface. So there's a 90-degree angle between them. So everywhere. So that's cosine of 90 is 0. And inside here, where there is no field. So the E dot dA is 0 because you got a dA, you got that surface over here, and you got part of the cylindrical surface, but you don't have an E. So for sides 1 and 2, this flux is 0. So the total flux, which is the sum of the flux of all 3 sides, is only equal to the flux of side 3. And I kind of jumped into this without actually saying that again. We did it yesterday, I think, but so it's just side 3 that I'm evaluating here. And in the end, you get sigma over epsilon. And it's just that. Now, I just did that side, but if you go to the other side, obviously it's symmetric, so you're going to get the same thing. So, yeah. Now, in the case of a non-conductor, same that does not have charge on the inside,
you're going to get the same answer. Because and you have to go through steps 1 and 2 and understand it's basically step 2. Understand what is the field distribution, what is the charge distribution, and what is the field distribution. If you didn't evaluate that, you might just, without thinking, go ahead and put the box over the whole thing. Not thinking about the fact that the field distribution, even for a non-conductor, because I almost screwed it up. Thinking about what happens on the inside, even though there can be a field on the inside, since you have uniform charge distribution on both sides and it's the same charge distribution, then you're going to have cancellation. Now, if they give you a problem where you got two different charge densities, because you could, right? You could have a non-conductor where you've got 2 sigma over here and 1 sigma over here on that surface. Why is that? Because for a non-conductor, and I illustrated this to you on the first week, for a non-conductor, wherever you place the charge, it stays there. It cannot redistribute. It doesn't have any free charge to act like the Borg to communicate and do its thing. Can't do that. So I could put 3 sigma over here and 1 sigma over here, and in which case, there will be a non-zero field inside because over here, only one sigma is going to cancel out. So basically, it would be a stronger field over here than here, but there would be a field on the inside because not all of the field lines would cancel. And so therefore, I would have to go in and get, both sides. And, but, that actually is a really nice problem. I didn't think about that. If I was, I might start to kind of infuse some of my own problems into the test that I'm giving you, getting these problems elsewhere, because I can do that. It's a lot of work though. But like a problem like that, because you're not going to get just, it would be something different than the answer that we are going to get for this when it's equal, which is sigma epsilon. And it's really a qualitative. You got to understand that before you even start applying Gauss's law. So steps 1 and 2 of the way I laid it out for you can be very important. You want to spend time really thinking about it. Anyway, it is equal. Fields do cancel on the inside, and so we only have to place the Gaussian here. So ultimately, it would lead to the same answer for this situation, where the electric field would be equal to sigma plus over epsilon naught, this guy. Now for this guy, not so much, right? Non-conductor, uniform charge density. Oh, I guess it's negative. But here, it's not going to be surface charge. It's got to be volume charge, right? Sigma minus, where that's going to be equal to, some, charge per unit differential volume, right? So just have it as a different definition. And, I go through, I apply Gauss's law, but Gauss's law still talks about the amount of flux through the surface, through this cross-section area. Now, and if I had a 2-dimensional, just remind you, well, I've done it. You can go back and look at it. If you looked at the 3-dimensional view, again, this is a pill box. So there's a little circular cross-section area that is incorporating the charge enclosed inside the whole thing. Now, for this one, oh, that's the national alert test thing going on. Yeah, it talked about this the other day, Monday. We got a national emergency alert thing here. Yeah, coming through your phones. So yeah, what time is it? Yeah, 11:30 or 11:18 something. Okay. Yeah. All right. Is it going to come or is it? This is the test now. The purpose is to maintain and improve alert warning capabilities at the federal, state, local, tribal, and territorial levels, and to evaluate the nation's public alert and warning capabilities. No action is required by the public. Okay, cool. All right, got it. Where was I? Yeah, so if we apply Gauss's law to the non-conducting plane that has uniform charge density rho all throughout the thing, still, well, here we got three surfaces, 1, 2, and 3, we'll say. Surface keep them the same. So I call this side 1, I think I did. This is side 2, and this is side 3. So 1 is still going to have 0, a contribution to flux, because the areas like this, the field, well, actually, is that true? That's actually a bit more interesting now. Hmm. You know what? That's actually a bit more complicated than I thought. This is probably why I don't have that one in the book. Wow, I got it. Wow. Yeah, that's complicated. But I think I worked it out. You are not going to have a field along the vertical. Everywhere along the vertical, the field is, there's no field that points in that direction. Because if you think about, let's come over here. Let's think about, like point charges. Is kind of lined up like that. So each point charge is going to have a field doing something like this, radially. But each one of them do that. And you can see you're going to have cancellations. So all of the components that are vertical will cancel out. Only the components along the horizontal will add. Because no matter how far you go above, like in any region that you take, no matter how, if you talk about extreme, length, like, at every point you could incorporate more of charge above or below. So the vertical components, there'll be enough to actually cancel out the field at every point. But in terms of, maybe I didn't say that very well, but just think about it. In terms of the horizontal, the only place that that will happen is right in the middle. So when you're right in the middle, there's enough charge on either side to cancel the field right at that point. But when you start to shift over, now there's going to be more charge on this side or in that length than over here. So you start to see a little bit of a field, where if it's negative, it's pointing back in that direction, but inside the material as you get farther away. And that just increases as you go outside, right? Yeah, but so yeah. Oh, right. Yeah. So it's not like outside the field is constant, but inside it won't be constant. Inside it will not be constant. It's a constant on the surface, and it decreases to 0 in the middle, then starts decreasing back up to this value that we're going to figure out on the surface, which is, I guess I would call it, I still think we have to define it in terms of rho. So I think it would end up being rho over 2 epsilon. But yeah. So it's interesting if we could use Gauss's law to figure out what the functional form looks like on the inside, how it decreases. I'm guessing it might be linear, but I'm going to do that in a second. So yeah, so if I've done this correctly, what I would say with the problem we're doing now is, outside the surface, outside the material, you only get flux from this guy and this guy. You get 0 flux from here because of there's not going to be there will be a field, but the field does not have a vertical component. Well, it only has a horizontal component everywhere inside. And so the flux through the cylindrical side, 1, is going to be 0. That's my final solution. So I'm going to say a flux 1 plus flux 2 plus flux 3, and flux 1 is 0. That equals charge enclosed over epsilon naught. So in the end, you have the two surfaces, EA, E is 0, 0 here, you add them up. Basically, the field is pointing basically like that through that surface. But A, or dA for surface 3, is pointing like that. So here you get actually 180 degrees. And so that kicks out a minus sign, but that's just telling you that the field is pointing opposite. It's flux into, the total flux is pointing, you got flow into the surface as opposed to out. And same over here. And you're going to have 2 of them. The field is constant on the surface. So in the end, that flux is only going to be the value E times whatever the area of that Gaussian is, the cross-sectional pillbox portion. So you get 2 of them, EA from this, EA from this. So in the end, you get 2E times the area of the Gaussian equals. Now we have to do it in terms of charge density. That's really weird, yeah, because now I got to do, it's got to be a volume charge density. And if it's a volume charge density, well, I probably would have been specified the width of the Gaussian. I would know that. I would have to, so let's call that a D. I'm not sure I've ever done this problem. Give it to you in class. I don't remember it. Because now this charge density has got to be, so the charge enclosed is going to be equal to rho times delta V. That's going to be rho, and the volume, well, of delta V meaning just the volume of the Gaussian. So I'll make that volume of Gaussian. And the volume of this Gaussian, is pi r squared, pi. So it's whatever the radius of my Gaussian is, the pillbox. So I would have to specify that. So that would be like a pi r squared times d. Well, that's it, that's the volume. But then the area of the Gaussian would just be, the area of the Gaussian would be pi r squared. Yeah. Yeah. So that here I'm going to get the charge enclosed is this. So that's going to be rho pi r squared times d over the area of the Gaussian. So that's just that. Yeah. Yeah. So let's say rho times the volume of the Gaussian over epsilon naught. Let me number these equations. I started with equation 1, and then I went to equation 2 here to work out that. And call that equation 3. Solving for the charge enclosed. Charge enclosed. Oh, wow. So equation 1, 3, and this is going to be equation 4. So that's messy. I'm going to have to do this over here just so it's clear for me what I'm doing. Messy. So starting again. The flux is going to be due to the 3 sides we just went through. So the total flux to the side 1, plus flux to the side 2, plus flux to the side 3. That guy is 0. And from each of these, we get, this is charge enclosed divided by epsilon naught. And this we get EA 2, I'm just going to call it Gaussian, plus EA Gaussian equals charge enclosed divided by epsilon naught. What's up with these pins? I just filled them up, didn't I? So I get 2 area of the Gaussian, but then equals charge enclosed divided by epsilon naught. But now, 2, 3, 4. But now rho is equal to the charge enclosed divided by the volume of the Gaussian. Now, again, you might have forgotten the side view. Let me come over here and draw the side view so you can see it a little better. So the side view, we have a pillbox. This thing here is a cylindrical pillbox like this. And then it goes into the, like that. And then here it cuts through. So the area we're talking about is this thing, which has a radius. Because, it has a radius. And it's, whatever its radius, let's call its radius, that distance is, that's what I'm calling R. And, there's charge here on the thing, but the only charge we're worried about is just that charge on that circular portion. But And the flux is the flux through that cross-section area right here. You know, like it's cutting out through the, you know, to the face there, which looking at the side view. And so that area is pi times r squared. But now here, when you look at the volume of a cylinder, the volume of a cylinder is basically the area times, and if you had infinitesimal thin slices, that area all the way through, that would make the volume of the tube. So you're just multiplying that area times d, and that's how you get a volume. So that's going to be equal to the charge enclosed over the area pi r squared times that distance d. So that the charge enclosed, that's what I had written over there. But I think a lot of it I was doing in my head, so maybe you didn't see it. The charge enclosed is equal to basically rho times pi r squared d. So that's what I'm going to stick into here. So now what I have is, oh, I forgot the E over here. I've got 2E. I just go ahead through and divide it through. Actually, E equals divide through the 1/2 area of the Gaussian, then times charge enclosed, which is rho pi r squared d over epsilon naught. But the area is pi r squared. So that's going to be 1/2 pi r squared times rho pi r squared d over epsilon naught. And so the pi r squared is canceling out. That goes, that goes. And what I'm left with the final answer is this thing. I've got the electric field is still going to be constant, but not quite the constant I thought. It's going to be rho over rho times d over 2 epsilon naught. That also does make sense because we know that the electric field has to have units of meter, you know, something over a meter squared. Basically, coulombs per meter. It turns out to be electric field is has units of it's not so obvious from there. But rho has the units of charge per meter cubed. And so without looking at the epsilon, because it has units as well, I can see that this thing right here is going to be charge per meter squared, which yeah. So that'll tell you that that's the right units, because kq over r squared, k is just 1/4 pi epsilon naught. So the units of k are the inverse units of epsilon. And so you have inverse units of epsilon times coulomb per meter squared, and you can see it works out. I've got coulomb per meter squared here, and inverse units of, well, epsilon, you know, in the inverse units of epsilon. Well, yeah. So that's it. That's the right units. So I think that is the right answer for this problem. So we still have a constant field, but this is what it would look like in terms of uniform charge density. Yeah, I don't remember doing that problem. I mean, we just made it up. That's interesting, though. But that's why I like Gauss's law. Like, this is a pretty complex problem, you know, having to do it with
Coulomb's law, I don't even know how I would work that out. Coulomb's law.
But even with Gauss's law, that's the hard thing in there, because with Coulomb's law, you'd have to actually integrate all that and show that there's no vertical field, no vertical component of the field. With Gauss's law, it just causes you to think about how the charge is interacting. And what I normally do is I break it down to point charges and try to look at a point charge configuration. So if you got point charges lined up like that, you can see that the vertical field is going to cancel out, even if you just went individually. And even the side fields, like you're going to have enough where they cancel out. Well, the side versions, basically the vertical component of the side, like for example, here you got like a line going out like that, then like that, right? But over here, let's make it a different color. You're going to have something doing something like that, and then like that, like that, right? So what's going to happen is, and also down here, and up here, you got something like going down like that, right? So the one on the other side up here has a field going down like that. So ultimately, you can see that the vertical components are all going to cancel, and you're only going to get contributions on every level of the horizontal components. So that, yeah. So you go a long way with just qualitatively extrapolating. And then once you figure that out, then you can look at on the horizontal and see, okay, is it constant there? Is it changing? What's happening? So yeah. Got it. It's linear on the inside. It's linear. It's linear. It becomes a linear change. What time we got? Oh, we went over. Well, I think I didn't start lecturing to 30 minutes in anyway. So let me give it just a few more minutes. But I just realized, since I got it fresh in my mind, I know how to find the field. So now that's the field on the outside. Everywhere on the outside, you're going to have that, and it's constant. The field would look, it would look like that. Not changing its value even as you go out to infinity. And that's the magnitude. So we say E out. What about on the inside? So let's come over here. Take a look again. Blow it up and make it pretty large. So we got these charges, distributed over the thing. Whatever. Now we've already qualitatively determined that along the bisector, the center of the field is vertical fields are zero, so we only have a component in horizontal direction. Let's make this like our axis here, okay? And we're still going to use a pillbox, but I'm going to center the pillbox at the origin, and the pillbox will only go out to a certain distance, x. Now remember, this total distance right here is a constant, that's d. So basically, 1/2 is d over 2, the other half is d over 2. But here, I'm going to make this x. I'm going to say that this is my x-axis, right? So I'm going to make that position, basically, that becomes x. So basically, my pillbox has a length of 2x. A length of 2x. And its cross-section area can still be pi r squared for the reasons we mentioned earlier, like the the pillbox portion. So basically this is plus x, and this is minus x, the distance, going in either direction, right? Plus x. So the pillbox its length is 2x. So now let's apply Gauss's law. Really messy over here. To the pillbox on the inside. Now we still have three surfaces. We'll name them the same. I think I call this side 1, side 2, side 3. I'm arguing that for the reasons we mentioned earlier, the flux of side 1 is still going to be 0. So flux 1 plus flux 2 plus flux 3, that guy is 0. From these two sides, we still just get to A, where A is the cross-sectional area of those sides of the Gaussian. They're still circular. But the charge enclosed I'm going to still be able to substitute in this thing here, where rho is the charge density is uniform, but it's also the charge per unit volume of this new Gaussian now. But the area of the new Gaussian is going to be, so when I write down rho, the charge enclosed is going to be, so I still have the 1 over epsilon naught here, but then I have times the rho, then times the area of the, of the side, the area of the Gaussian, which is pi r squared, but then the length of the Gaussian is 2 times x, not d now, where x is a variable because I could put it at different places, 2x. Okay, that's it then. So now, and I forgot the e out here. So now the e is going to be equal to, divide through, I have 1 over 2a, so that's 1 over 2 pi r squared times 1 over epsilon naught times rho pi r squared 2 times x. And so there you have it. You're going to get 2 pi r squared here, canceling 2 pi r squared here. And my final answer is that now the field is not linear. The field is not constant. It's linear. It goes as x. It's proportional to x and is equal to rho over epsilon naught times x. And that makes sense based on how I qualitatively described it earlier, that at the surface, the field is this, but then as you move toward the center, the field decreases and it's 0 right in the middle, and then it starts to increase with an opposite direction back on the other side. So they should match up when you get out there. And when you get out to the side, I think I've defined some things differently from this side as opposed to that side. So here I said the total thing was I have 2 sides. That 2 still comes from the 2 sides. Oh, yeah, because it's redefined, because here, I define the whole thing as D. But here I'm just defining the length as X. So the reason that it doesn't look the same is because I should have, in the old problem, I should have defined it's 2 different definitions. In this definition, D is equal to 2x, but I didn't have an x in the other one, so I should have defined it as D just being half the distance, the total distance. So if I had made that D, then up here I would have had a 2D. And so then those 2's would cancel. That's why they don't look the same. So you got to be careful about that kind of stuff as well. There's two different definitions for the length. So whatever. Because basically when I get out to, right? Yeah. Because I'm saying that on the surface, the field is going to be here, it'll be rho d over epsilon. But in this, the way I define it, when I get out there, that's just going to be d, not 2d. So I would have had, for this thing, the field at the surface being rho d over epsilon naught, and over here, I would have had rho d over 2 epsilon naught. And that's because I got to be careful. How I didn't define those horizontal, I didn't define the horizontal coordinate in the same way for both problems. But now, if you do, they match up. Or I guess I could have kept it the same, I guess. Maybe because I didn't take in consideration the other side. So maybe I'm overthinking it. Yeah. Uh yeah, I guess, yeah. So if this is D, and I said this was 2, yeah, that's the surface. But I gotta remember, I'm not just expanding to one side, I'm making both go out. When I expand the length, I'm doing it symmetrically. So on the surface, I would have I have to go back, I'd have two contributions from but I always have two contributions from the flux, but yeah, I think that is the case. I think that I would have to redefine D as half the distance, because that's what I'm saying this is. X is half the distance, so distance is distance. I'm saying the length is, yeah, that's it. And the last one I said the length was D, and here I'm saying the length is 2x. That's the problem. So I am right. I have to go back and redefine that distance as 2D, where D is just the total length from 0 to the edge. So in that case, that they would match up. So I did. That is an issue. You have to go back in that last problem and redefine it. So my bad on that. Okay, well, cool. That's the end of chapter 23, Gauss's law. I don't think you're going to find that problem in there. I'm pretty sure, I'm very confident that my final solutions here are correct, but it's interesting that I don't know why I never thought to do a problem like that before. I guess because it's kind of, I don't know. I thought I had, but I hadn't, because I would have remembered. And, but this is the kind of thing you have to work with Gauss's law. And, maybe it's a little bit, I think it's a little bit subtle and complex, but not mathematically. It's complex physically. And I'd rather spend my time working through physics than working through mathematics. To do Coulomb's law to get this, it would be an absolute nightmare for me. And in the end, why bother? You're going to get the same answer. So, yeah. All right. Well, thanks. And told you I'd give you your time back. I'm pretty sure we're squared up now. And yeah, so that's class dismissed. Go ahead and I guess I will go ahead and open up chapter 25 for you. I think I've opened up. Yeah, I did open up this homework already. But I'll go ahead and open up the basic homework 4 and quiz 4. so that you can maybe start on that early into next week. All righty then. Thank you, and class dismissed.